Let's do a few examples of double integrals in polar coordinates. Let's firstly convert and compute this integral. So firstly, I've plotted y equals, y starts at 0, goes to this function here. So we're integrating like this. Between x equals -1 and 1. So it's this semicircle. Semicircles lend themselves to polar coordinates very easily. So you note that the radius goes from 0 to 1, and theta goes from 0 to pi. So we can recast the limits 0 to 1 in r, 0 to pi in theta. We're doing dr first, but remember dx or dy dx, the area element in Cartesians, becomes this in polars. We then have to convert x and y, the integrand, and we recall that x equals r cos theta, y equals r sine theta, and the trig identity cos squared plus sine squared of any number equals 1. So x squared plus y squared equals r squared cos squared theta r squared sine squared theta. Obviously, we can apply this trig identity, and we're just going to get r squared, which is what we expect from trigonometry anyway. So our integral becomes the integral of r cubed, right? So we've got this r here, over this region, 0 to 1, 0 to pi. So we can do that very easily. 0 to 1, 0 to pi, r cubed dr d theta. Integrating with respect to r gives us 1/4 r4, or 4 over 4 between 0 and 1. We've then got to integrate that with respect to theta, but that's just going to give us 0 to pi 1 over 4 d theta, like so. And when we integrate with respect to theta, we're going to get theta on 4 between 0 and pi. So that whole thing just works out to be pi on 4. Okay, so that's one example. Let's just compute this example here. It's already set up in polar coordinates. This is what the function looks like, by the way, or the region. In theta, we're going from minus pi on 4, which is down here, to pi on 4, which is up here. And if your r equals cos 2 theta, you fill in this region here in space. All right. So we've just got to integrate this. There's nothing particularly difficult about this. We don't have to change coordinates, nothing. We just start doing our integral. So r goes to r squared on 2 between 0 and cos 2 theta. We haven't done the theta integral yet, so it's still like so. So this is going to become pi cos squared 2 theta on 2, like so, d theta. And now we're going to have to use a trig identity to be able to compute this integral. That trig identity is, and you can just look this up on Wikipedia. So there's half there, so there's a factor of a half into 4. 1 plus cos. It's the squared to 2. It's the double angle formula. So this now goes to 4 theta. There's another factor of 2 like that. d theta. Be careful with the signs and the plus and minus on these. I tend to get them wrong if I do them from memory. Okay, so now we've just got to go ahead and do this integral. Equals 1/4 into, so I've taken out the factor of 2 there to multiply with that factor of 1/2 there. Integral of 1 with respect to theta is theta. Integral of cosine is sine, and we've got to take care of this 4, so we're going to get plus 1/4 sine 4 theta between minus pi on 4 and pi on 4 like so. Now this is going to yield when we plug everything in. This goes to pi over 8. All right, so 1/4. Right, so sine pi is 0, obviously, minus pi on 4 minus plus 0, whatever. So that's pi on 8. Because that goes to pi on 2. All right. The last one we're going to do is this problem here. Integrate some f of xy over this region, x squared, or x minus 1 all squared, plus y squared equals 1. So let's sketch that region first. So it's a circle, but it's centered at 1 in x and 0 in y. So it looks like this, right? So this is our region of integration. Now it's a circle, so we should be looking to use polar coordinates, but it's not actually immediately obvious what the equation is in polar coordinates for the region. So let's write down that we recall x equals r cos theta, y equal r sine theta, and we substitute that into our region. R cos theta minus 1 squared plus r squared sine squared theta equals 1. So r squared cos squared theta minus 2r cos theta. Have I got this around the right? Yes, I do, I believe. Plus 1 equals 1. So we can now start simplifying this. Implies, so obviously this 1 is going to cancel with that 1. We can use sine squared theta plus cos squared theta equals 1 to obtain r squared minus 2r cos theta equals 0, or r squared equals 2r cos theta, r equals 2 cos theta. Okay, so that's our radius, and our theta is given by we start at well, we've actually got a choice with how we can describe theta. It's easiest to describe theta as being from pi on 2, so here, to minus pi on 2 down here. So what we're doing essentially is we're sort of sweeping out our radius in a different way, right? We're starting at radius 0 here, going up to radius 2 cos theta, and then we're rotating around half of our circle, right? So we're kind of scanning out the top half and then rotating it around by pi on 2. Or we're rotating it around by a distance pi. So we set this up, our integral, I equals minus pi on 2 to pi on 2. And obviously the limits of this work out. 0 to 2 cos theta in R. We were given some function. We're not actually told what the function is. So that's just f of R cos theta R sine theta. Just substitute x and y. R dr d theta. All right, so that's how you figure out, or that's a more complicated example. You just have to be very careful in describing your regions.